Okay, last time we have touched base a little bit about that log function. We know how to convert from log to exponential form, and then from exponential form to logarithmic form. Now, once we know how to do the conversion, then we will see that log function is actually the inverse of exponential function. Now, what is important for this one statement, that log function is exponential function, actually comes in point 234. Using the fact that log function is an inverse of exponential function, then we will be able to see first the domain, second to graph basic log functions, and then later on the transformation of that. Finally, then we will be able to solve some exponential function using logarithmic. Okay, let's go on first with note that log function as the inverse of exponential function. Let's say, for example, I think this, instead of an example, I'm supposed to show that as a proof. Let fx equals to b to the x. Now, we have seen that from the graph that we see that it is a one-to-one function. We have seen that y equals to b to the x is a one-to-one function. For b positive and not 1. Okay, now then find the inverse function. Step 1, I change the fx becomes y. Step 2, I swap the x becomes y, y becomes x. Step 3, I need to solve for y, and to solve for y, I change that exponential function into logarithmic function. So y equals to log base b of x. And therefore, step 4, our inverse function is f inverse x is log base b of x. Okay, so yes, log function is the inverse of exponential function. Now, one of the big consequences is the following. So if we compare fx equals to b to the x, and the inverse, let me call that gx equals to log base b of x, then we remember from last time the domain of the exponential function is what?
All real numbers.
It's all real numbers. Now this domain, when you do the inversing, that domain will become the range. The range of a log function is a real number. Now, the range of exponential function, which we know to be from 0 to infinity, right? That's the range. Now, that in our inverse function will become the domain. That will become the domain. So basically, then we can say that the argument of the log, the argument for the log should be that the argument has to be strictly positive. Okay, if I combine these two ideas here, then x has to be strictly positive. Okay. Now, furthermore, the y-intercept for exponential function was 0, 1, is 0, 1. Now that will become our x-intercept in logarithmic function. That would be 1, 0. And in the exponential function, we don't have x-intercept. So when we go to the logarithmic, the inverse function, then we won't have the y-intercept. In the exponential function, we have horizontal asymptote y equals to 0. Okay, now then when we go to logarithmic function, that horizontal asymptote becomes a vertical asymptote. The y becomes x. Okay, now basically we will end up having the reflection of the graph of exponential function with respect to x equals to y line. Let's take a look on this graphing board.
I have a question.
Uh-huh.
So the y-intercept is always 0, 1
The y-intercept for b to the x.
for b to the x.
Uh-huh.
It's always 0, 0, 1.
Just think about it. If you replace the x by 0, what happened?
Ah, yeah.
Right? Uh-huh. Mm-hmm. Y equals to, I need to give me a second. Keypad. I need the log. Now, this is the graph of exponential function and logarithmic function. Are you looking at my graphing board?
Yeah.
Yes.
Yeah.
Okay, good. Now then, you see the purple curve. The purple curve is my exponential function with base 2. Okay, and my red one is logarithmic function with base 2. And then the reflection is done with respect to y equals to x line. Second, y equals to x line. Okay, every time we do inverse function, you reflect that with respect to this blue line, y equals to x. Okay, now if we see even further, let me copy this graph and put it back to our node so that we can see that better. Now you see that, let me write it down, that this is y equals to 2 to the x. This is y equals to x line. And this is y equals to log base 2 of x. Now, remember the three important coordinates. The three important coordinates that we have in exponential function is the y-intercept 0, 1, and then 1 comma b, in this case 1 comma 2, and negative 1 comma 1 over 2. These are the three important coordinates. When we reflect them with respect to this line, the y-intercept becomes x-intercept, right? You have to memorize this though, okay? Now, and then 1 comma b, 1 comma 2 in this case, being reflected becomes 2 comma 1. Okay, and then negative 1 comma 1/2 being reflected becomes 1/2 comma negative 1. Okay, so this is 0, 1, 1 comma 2 because the base is 2, and then negative 1 comma 1/2. When you reflect that with respect to x equals to y line, it becomes 2 comma 1, 1 comma 0, 1/2 comma negative 1. Okay, now from the graph, you can also see that the domain of this log base 2 of x is all a positive number. It has to be a positive argument. This x here has to be strictly positive. That's for the domain. Now, so from here, from the conclusion that log function is the inverse of exponential function, we actually get two things. We will be able to answer the question for the inverse of exponential functions. Actually, I can add into that. We can find the asymptote also later on. Okay, we can find the asymptote for any log functions. And then second, later on, we will be able to sketch the graph for logarithmic function. Okay, I think for today, we will spend most of our time on this part here. Now, let's see, for example, on the issue of the domain. So, domain of y equals to log base b of blah is the set of all x where the blah is positive. Okay, now keep that in mind. So, for example, let y equals to log base b of, let's say, 3x minus 2 over 4x minus 5, maybe plus 5. Now find the domain. What we do is we set the argument to be strictly positive. Okay, so the solution, the argument 3x minus 2 over 4x plus 5, this has to be strictly positive. Okay, now then how to solve that? It's non-linear inequality. It's a non-linear inequality. So I need to do it in 3 steps. Step 1 was the critical numbers, right? I hope you remember that. I believe I penalized you enough number of points that you now know you have to write that 1, 2, 3.
Yes.
Right? Okay. Now, why you have to write that 1, 2, 3? Because there are details in each one of them, especially in step 2. Okay. I don't want you to jump the steps and then later on get the answer only by luck. No, no. Once you make math into kind of like a guessing game, then there's no more organization there. Okay, so critical numbers on the numerator, we have x equals to 2/3. On the denominator, we have x equals to -5/4. And then step 2, the sign graph. -5/4. And then 2/3. When x equals to 2/3, I get 0. When x equals to -5/4, I get undefined. And then I think this will be positive, negative, positive. Yeah. I actually I use this the edge of my eyes. Look at the y-intercept for this expression here. You see the y-intercept is -2/5, right? Okay, so when x equals to 0, then the value will be negative. Okay, I don't need to explain this to you actually, but I hope you know how I can get it so fast. Okay, and then for step 3, I need the positive part. So the domain will be -infinity up to -5/4 union 2/3 to positive infinity. Is it okay?
Yeah, could we have used the properties of logs to
Actually, no, you can't. You can't use property of logs, even though that's something we will talk about in 5.4. Okay, there's a weakness with that property of logs later on, and I will explain it to you later on why we are not supposed to use that one.
Yeah.
Okay.
Okay.
But let me explain it later. Now, then for part B, suppose find the asymptote. To be more precise, the vertical asymptote. Okay. Now then, if we look back to our original function, log base b of x, okay, log base b of x, you see the asymptote happens at vertical asymptote x equals to 0. Right? Okay, so if you want to get the vertical asymptote, what you can do is you set the argument, the x here, the argument to be equals to 0. Now then, what is the vertical asymptote here? The vertical asymptote is when 3x minus 2 over 4x plus 5 equals to 0. That implies the vertical asymptote is x equals to 2/3. Okay. Now we don't know what the actual graph of this, what's the actual graph of this log function here. We don't know what's the actual graph, but we know that at least we can find the domain and find the range. Out of curiosity, I would like to know what they look like too. I mean, what's the graph supposed to look like? So let's take a look. What base did I use? I don't remember what base did I use. Base b, let's say the b is 2. Okay, log base b of what's that? 3x minus 2 over 4x plus 5. That's what it looks like. You see, we have this vertical asymptote here. I think the vertical asymptote is at 2/3. It seems like we have vertical asymptote here. Oh, that's when it is undefined. I'm sorry. That's when it is undefined. I forgot to deal with that. Yeah, of course, that it becomes undefined at. Sorry. I need to go back here. I need to fix this one. the thing is like this guy give us asymptote to start with. So that's another asymptote. I forgot to mention that. X equals to negative 5, 4. Okay, so there are two vertical asymptotes. When x gives undefined and when x gives 0. Okay.
What's the negative 5/4 for? I didn't get it.
Because it makes the denominator in the log, the argument, becomes undefined.
Oh yeah.
Right? When it is undefined in our rational function, it gives
Yeah.
us asymptote. Okay, so it already becomes asymptote even before you put the log in.
Oh, okay.
Yeah. To make sure that we get the correct one, let's see. I get y equals to I'm sorry, x equals to 2/3, and then x equals negative 5/4. I hope you can see that better now. Right? I can zoom this in though, and you see that it seems like it touched the other x, the other vertical asymptote, but it's not. It converges very, very close, really fast, but it's not touching it. Not supposed to touch that stuff, right? Okay. You see, right? I kind of like go really deep already, but I hope you see that there are two lines there, quote unquote, two lines instead of identical lines. Okay. Now let's go back to our notes. Okay, so if this is the equation, then to find the domain, we need to set the argument. We need to set the argument to be positive. Okay, we set the argument to be positive. And then to find the asymptote, we set the argument to be 0. Now don't forget, besides being 0, the denominator can screw us up too. Okay, that's why it forms another vertical asymptote. Now that's for the domain and asymptotes. In the past, I never asked the asymptote question. I don't think I will ever ask that question anyway. Okay, but even if I do, that would be a bonus question thingy. Now, the one that we will focus, I think it's quite easy to find the domain of log. Just remember that the argument has to be strictly positive, and then you solve it from there. Okay, the one that gives us a harder time is how to graph. The one that gives us harder time is how to graph log function, at least the basic log function. Graphing basic log functions. Okay, let's say, for example, let's call this example 2. Is it example 2 or example 1? No, not example 1. Example 3, I should call that. Example 3, let fx equals to log base 3 of x. So what's the domain? The domain is from 0 to infinity, strictly positive. The range is all real numbers. Okay, and the y-intercept notice that this is the inverse of 3 to the x. Okay, so to answer the y-intercept for the log base 3 of x, we need to answer the x-intercept of 3 to the x.
1, 0, comma 1.
What is the x-intercept of 3 to the x? What is the x-intercept here?
It doesn't have one.
So the y-intercept in the log also doesn't have 1.
Oh.
Okay, now the x-intercept here, we look at the y-intercept for 3 to the x. The y-intercept here was 0, 1, right? Okay, now when you do the inverse, it becomes the x-intercept, 1, 0. Okay.
Professor, I think it should be the other way around.
Hmm?
I think it should be the other way around.
What do you mean?
When y is 0, y is never 0 for a log.
Yeah, y can be 0 for a log.
Oh, y can be 0?
It's okay to be 0 for a log.
Oh, okay. Sorry.
Yeah, see, like, well, just think about it. Okay, log base 3 of 1 equals what? Let's call that x.
Mhm.
So 3 to the x equals to 1, so x equals to 0. Right?
Okay.
So log base 3 of 1 is 0.
Oh,
Right?
yeah.
Now then, a bit further, the vertical asymptote. Then we look at the horizontal asymptote here. The horizontal asymptote here is y equals to 0. So the vertical asymptote will be x equals to 0. Okay, it would be nice if you can memorize this. If not, then well, then it takes you slightly longer later on. But eventually, right before you take my test later on, you need to be able to do it fast enough. Okay, very soon you will see the reason. Okay, let's say we try to sketch the graph. Tick 1, 2, 3, 4, 5, and on. Now we have 1, 0 as the x-intercept. Okay, and then we have vertical asymptote x equals to 0. That's the vertical asymptote. It's exactly the same to the y-axis, so they look coincide. Okay, but what else can we plot to help us graphing this? Then you need to remember those 3 important coordinates we have in the exponential form. The 3 important coordinates 0, 1, 1, 3, negative 1, 1/3. 1, 3, negative 1, 1/3. Now, why do I need those? Because when I do the log, I basically reverse the x and the y. X becomes y, y becomes x. So 1, 3 later on in the log becomes 3, 1. Okay, negative 1, 1/3, negative 1, 1/3 becomes 1/3, negative 1. Now then, using these 3 coordinates, I can at least get the graph of that log base 3 of x better at the position where they bend the sharpest. Okay, these are the 3 important coordinates that I need to have on the graph. Okay, let me ask you to do one problem. This time I make the base to be between 0 and 1. let's say example 4. Example 4, I want you to have let gx equals to log base 1/2 of x. Now I need you to answer these 5 questions together with the sketch of the graph. The domain, the range, y-intercept, the x-intercept, and the vertical asymptote, and then the sketch of the graph. Okay, now let me give you 1, 2, 3, 4, 5, 6, 7, 8 minutes from now. Done. The domain will be just like before, from 0 to infinity. The range is all real numbers. The y-intercept none. The x-intercept is 1, 0. The vertical asymptote is x equals to 0. Now the graph requires us to do, let's see, the graph will have the same x-intercept, 1, 0, the same vertical asymptote, okay, but with only these 2 informations we cannot graph better. We need to kind of imagine what it looks like, what the 1/2 to the x looks like. Now 1/2 to the x will look like 0, 1. Because the base is less than 1, so the graph is actually going down. We have this guy and we have that guy, right? This is 1, 1/2, and this guy here is negative 1, 2. Okay, now then using those 2 coordinates, 2 extra coordinates, then we get 2, negative 1, that's 1 coordinate, and then 1/2, 1. Okay, now, using those 3 coordinates, then I get the graph. Actually, you can go even further. If you happen to realize that one other coordinate you have there is actually negative 2, 4, right? Negative 2, 4, right? So this would be 4, negative 2. Like that. Okay, now that's log base 1/2 of x. Actually, we can say a little note. Let me put that note here. We can say a little note that if for b to the x, the graph will be increasing when the b is greater than 1, decreasing when b is less than 1, between 0 to 1, right? Now the thing is, it turns out that the same increasing, decreasing applies the same when we deal with log. So log base d of x will be increasing when the base is greater than 1. Now, for example, log base 3 of x and log base 2 of x, right? You see that it is increasing, right? If the original exponential function is increasing, then the inverse will also be increasing, okay? When the exponential function is decreasing like this, log base, I mean 1/2 to the x is a decreasing function, right? Okay, because it is decreasing, then the inverse will also be decreasing. Okay, now, but the one I need you to actually be able to really graph is not this type though. The one I need you to be really, really strong are this type. Example 5, let fx equals to, let's say, log base 2 of x plus 4 and minus, let's say, 3. I think I asked this function a lot in my test. I think I asked the same function at least 3 times. At least 3 times. But I hope you will see why I ask this a lot. Okay, now first one, how about the domain?
Are you asking? Or?
Yeah, how about the domain?
-4 to infinity.
-4 to infinity. Now, if you wonder why, that's because x plus 4 has to be strictly greater than 0. Right? Okay, and then how about the range?
-3 to infinity.
You sure?
Yes.
No, you see that the original log function, okay, it's the domain is already all real numbers.
Right.
Right? So when I move 4 units to the left, it doesn't change the range when you move it to the left, right? And then when you move it down 3 units, because it's already all real numbers, it won't change the range either. Okay, maybe I put it this way. Just to imagine what the graph looked like. Now, suppose this is our log base 2 of x look like. Okay, now then when I move 4 units to the left, why cannot? Yeah, when I move 4 units to the left, okay, it becomes like this, right? You see, it's still all real numbers.
Yes.
Right? And then when I move 3 units down,
oh, it's still all real numbers.
It will still all real numbers.
Yeah.
Right? Does it make sense now?
Yeah.
Okay. So that's the nice thing about having a range all real numbers. However you move it, it will be all real numbers. You know, the one that we are afraid of course, if you have a square inside that x plus 4, like for that x plus 4, let's say I change it becomes x squared plus 4, then it won't be all real numbers anymore, because well, the domain already strictly changed, right? Okay, but if the domain is inside the, if the argument is from 0 to infinity, in this case, then x is between -4 to infinity, then the range will also be all real numbers. Okay. So the range in this case will still be all real numbers. Now, how about the y-intercept? Now, as you can see, once we move this and there, then we may have y-intercept. Originally, it's not, right? Okay. In fact, as you have seen earlier, the graph later on expectedly looks like this, right? Something like that. Okay. You can see the domain. The domain includes 0. Include x equals to 0. So there must be y-intercept. Okay, there must be y-intercept. It must be 0 comma something. Now, how to find that 0 comma something? Then we plug in f0 equals to log base 2 of 4 minus 3. Now, what is log base 2 of 4?
Two.
That's 2. So this is equals to 2 minus 3, which is -1. So the y-intercept is 0, -1. This is the y-intercept. But the x-intercept, the y has to be 0. The y has to be 0. So 0 equals to log base 2 of x plus 4 minus 3. Can you solve this?
-3.
No, I don't think so. No, let's see, I move the 3 to the other side. That's 3 equals to log base 2 of x plus 4. And change it into exponential form. 2 to the power of 3 equals to x plus 4. That's 8 equals to x plus 4. So x will be 4. Okay, so the x-intercept is 4, 0. 1, 2, 3. Okay, and then part E, let me do it here. Part E, the vertical asymptote will be with that, right? Will be x equals to 4. Okay, so my x-intercept, let's see. I mean, not x-intercept, vertical asymptote. 1, 2, 3, 4. Approximately like this. That's the vertical asymptote. But with only 2 coordinates, it's not enough for us to graph the log function. Okay, let's find the other 3 important coordinates. The 3 important coordinates for log base 2 are 1, 0, 2, 1, 1 half, 1. So I would try to imagine log base 2 of x. The graph looks like this. Okay, looks like that. Now then use this graph, the movement 4 to the left, 3 down. 4 to the left, 3 down. So 1, 0. 4 to the left, 3 down. So that's the new location for 1, 0. This 1, 0. This 1, 0 here. Move 4 to the left and 3 down. Now it's here. Okay. And then 2, 1. 2, 1, move 4 to the left, 3 down. It's now here. And then 1 half, -1, move 4 to the left, 3 down. Okay, now, so I have these coordinates. In fact, I have 5 coordinates. 1, 2, 3, 4, 5. I think it's enough for us to graph it. Okay, so on the top of x-intercept and the y-intercept, I also have these original three important coordinates that I move 4 to the left and 3 down. Okay, that's how I get more coordinates. Now, let me ask you to try one problem. Example 6. Let fx equal to log base 2 of how about log base 1/2 instead? Change it. Log base 1/2 of x plus 2, and then minus 1. How about that? Okay, try this. Of course, you need to find the domain, range. You can do those by memorization, but for x-intercept, y-intercept, you need to do some computation. And for the vertical asymptote, I think that's on the easy side. Okay, and then try to sketch the graph. Okay, let me give you maybe 8 or 9 minutes from now. Okay, the domain is -2 to infinity. The range is all real number, I'm sorry. The y-intercept, f0 equals to log base 1/2 of 2 minus 1. Now, what is log base 1/2 of 2? What will that be? -1. Okay, so we get -2 here. Y-intercept is 0, -2. Now, if you wonder how we get that, then we ask log base 1/2 of 2 equals to what? Equals to what? That implies 1/2 to what power equals to 2? So that's 2 to the power of -what equals to 2 to the 1. So -what equals to 1. What is -1? Okay, I wanted to use x, but I don't want to confuse you with the other x that we have. Maybe we use b, let's say, or p. And you can see that p is -1, right? How about the x-intercept? And we show the work here. Let's say 0 equals to log base 1/2 of x plus 2 minus 1. 1 equals to log base 1/2 of x plus 2. So we get 1/2 to the 1 equals to x plus 2. That's 1/2, right? Minus 2 equals to x. So x-intercept will be -3/2 or -1.5. So the x-intercept will be -1.5, 0. Vertical asymptote x equals to -2. By the way, in your test, I need you to show this. And I need to show this for the x-intercept. Okay. Now then, how about the graph? Graph, we have, what are the coordinates? -2, 0, -2, 0, -2, and then -1.5, 0. The vertical asymptote is x equals to -2. Okay, and then let's use log base 1/2 of x. log base 1/2 of x looks like this. That's 2 comma negative 1, 1 comma 0, and then 1/2 comma 1. Okay, now then 1 comma 0 move 2 units to the left and 1 unit down, so it will be there. Two comma negative 1, 2 to the left, 1 unit down. Oh, we already have y-intercept there, so we are good. Okay, and then 1/2 comma 1 move 2 units to the left and 1 down. Oh, that's what we have also. Okay, then we can sketch the graph now, and it looks approximately like this, and that one here approximately. Okay, now that's for log base 1/2 y equals to log base 1/2 of x plus 2 minus 1. Yeah. What we did here, we basically combine what we know about log base 1/2 of x and then the transformation. Okay, now that's for the graph. Let's finish this section and then I give you a break. Solving simple exponential equations using log. We know how to solve log exponential functions, exponential equations already, but let's do more. Instead of waiting until this 5.5 where we solve exponential and logarithmic equations, let's do the easy one right now. Solving exponential equation using log. Let's say, for example, I take a look on number 34. Solve 10 to the 2x minus 1 equals to 45. Now, in the past, as I remember in 5.1, we encountered the question where the base that we have here is the base that we can use for the constant on the other side. Right? Let's say on the other side we have 100 or square root of 10. Okay? If, for example, if this were square root of 10, I can rewrite that square root of 10 as 10 to the 1/2, and then they have common base that we can deal with. Okay, now in our situation here, the other side is not base 10 anymore, but imagine if that's a random number. In this case, it's 45. Then how do I deal with that? Change into log form. This is log base 10 of 45 equals to 2x minus 1. Okay, I will solve that further. This is log base 10 of 45 plus 1 divided by 2 equals to x. Now, we call this an exact form. We actually have dealt with exact form a lot, but this is basically the first time we call that exact form. What is the exact form? Exact form is the solution where we don't do any approximation, we don't do any rounding, and we leave it in log or maybe in square root. Let's say, suppose, for example, I have another function I have fx equals to x squared minus 3, and I ask you find the x-intercept. Then when you solve, you will get x equals to plus minus square root of 3, right? Okay, so we say x-intercepts are square root of 3 comma 0, and then negative square root of 3 comma 0. Okay, that's how we answered before. Now, square root of 3 is an exact solution. Okay, now then when you use calculator, after you use calculator, then you do rounding. I think this will be 1.7 something 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 something. Okay, and this guy is negative 1.7 something 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 something. I don't remember on the top of my head though. Okay, but let's say it's 1.7. Now the thing is, once you use calculator for that radical 3 is an irrational number, such that if you use calculator, okay, anytime you stop, let's say 5 decimal places, that's already approximation. That's not the real exact solution anymore. You already approximation, you already do some rounding. Okay, now that's the difference between approximate solution and exact form. Okay, that's the difference between exact form, in which we just leave it in log or in radical or in pi, for example. Okay, in e, for example. Okay, now that's exact form. Now suppose I need to compute this using calculator. I wonder if do you have your calculator with you? I would like to use your calculator to compute this. Now the base is base 10. The base is base 10. Now let's see what you get. Now you need to play with the parentheses a lot though. Let me show you my calculator. I use TI-84, but I think if you use TI-83, it will be quite similar. Now, I will compute log. You see that once I press log, it has parentheses right away. Okay, log 45. I need to close that parenthesis. Okay, log 45, whatever the value, and then I add 1. If you don't use parentheses, it may mean something different. Okay, but by writing it this way, log parenthesis 45, close parenthesis, plus 1 will give you the numerator, whatever that is, and then from there I divide by 2. Okay, so I get 1.32661. 1.32661. 1.32661. Is it okay? Now make sure you know how to use your calculator though. Make sure you know how to use your calculator. That's for number 32, 34. Let's see more. Is there anything else? I think number 36 is an interesting problem. But let's see. How about number 40? Number 40. E to the 3x squared equals to 112. The base is E, so what do I use?
Natural log.
I will use natural log, that's right. So it will be natural log of 112 equals to the exponent 3x squared. Okay, and then I divide by 3, so natural log of 112 over 3 equals to x squared. So x equals to plus minus for the square root of natural log of 112 over 3. Okay, now that's the exact solution, but we have issue with the 3 inside the radical on the denominator. Let me clean it up. I multiply by 3 on the top and the bottom inside the radical. Okay, so I get plus minus 1/3 square root of 3 times natural log of 112. Okay, so I have x1 equals to 1/3 square root of 3 natural log of 112, and x2 is negative 1/3 square root of 3 natural log of 112. Now, these are the exact solutions, exact form. Now, how about the approximate form? And you use your calculator. I see that x2 is basically the opposite of x1. So let me just compute the one for x1. 3 times natural log of 112, whatever that is. Okay, now how to do the square root of this number on your calculator? On my calculator, it's easy, but on your calculator, I don't know if you know how to use it. If you use TI-80, TI-30, if you use TI-30, do you see an answer button there? Anybody using TI-30 or 36? Now you usually see this answer button at next to the answer key, like enter, next to enter. Okay, but that's actually the second. So for me to get that answer, I need to press second first. Now my square root is here. You need to find it on your own calculator, but square root, because it's inverse of x squared, it's usually the second of x squared, usually. Okay, anyway, I will do the square root of this. So second square root, and then I want to get the answer. Second answer, enter. Now this is the square root of 3 natural log of 112. Whatever that is, divided by 3, 1.25413. 1.25413. So x2 will be negative 1.25413. Let me make sure that you know how to use that calculator. Do you get the same answers? Nobody say anything. Well, anyway, right now it's 5:50. Let's get the break. Come back at 6 o'clock. Okay, let's continue. We will go on to 5.4. In 5.4, we will learn properties of logs. There are 3 groups that we want to learn. Group 1, the basic properties. Second, the properties of log. And then the last one, the change of base formula. Now, change of base formula is especially being used to help us computing using calculator. Okay, but let's focus on the basic properties first, and then with the examples later on. Okay, let's start basic properties of log. The first one, I think I need to say for the base to be positive and not equals to 1. Then log base b of 1 is equal to 0. The proof, do the proof here, the proof. Suppose we call that log base b of 1 equals to x. Then what will x be? Then b to the x equals to 1, right? But we can write that 1 as b to the 0, right? Now, by one-to-oneness of exponential function, then the exponent must be the same. That's how we get that log base b of 1 is 0. Okay, so as long as the argument is 1, the value of that log is 0. Part B, log base b of b is equal to 1. The proof, maybe I use another color. The proof, using the similar technique, let's call that log base b of b equals to x first. Okay, now rewriting it as exponential form, b to the x equals to b, but b itself is b to the 1. So by one-to-oneness, x equals to 1. So log base b of b equals to 1. The third basic property, which is, you will see this third basic property is the generalization of the first two. What is that? Log base b of b to the n is equal to n. The proof, you will see the proof is very similar like before. The proof, let's call that log base b of b to the n equals to x. Then using exponential form, b to the x is equals to b to the n, right? By one-to-oneness, x equals to n. So log base b of b to the n equals to n. Now, the last part of these basic properties of log is b to the power of log base b of x is equal to x.
I'm sorry, could you go over C once again? I didn't see the relationship
From where to where?
from why you use bx equals to bn. I was
Well,
thinking
I just changed it into exponential form.
changing what into exponential. Oh, okay. Thank you.
Mm-hmm. Right? Okay. Now then, the last part of this basic property, b to the power of log base b of x is equal to x. What's the proof? Let's call that b to the log base b of x equals to y for now. So the left-hand side here, we call that y. Okay, we will call this y here. We'll call this y. Now, I want to show that that y is actually equals to x. Okay, now how to do that? Well, notice that this is actually an exponential form, if you think about it, right? Where log base b of x is the exponent, right? That's the exponent. So if I write it in logarithmic form, it will be log base b of y equals to log base b of x. Okay, now, but then we also know that log function is one-to-one. So log blah equals log blah implies blah equals to blah. So that b to the log base b of x is equals to y, which is x. Okay, our textbook actually mentioned this, but they don't really go over it. They don't really go over it. Not as I see, it doesn't even go over it in the exercise set. Okay, I think it's because it's way too easy. Okay, I myself call that basic properties of log because for that reason, it's so basic that you have to memorize it, and so little examples will be provided. Okay, yeah. But let's do some little examples. Why not? For example, example one, we have seen this before when we try to find the y-intercept of fx equals to log base 2 of x plus 4 minus 3. That was one example we have before. Okay, now then when we try to find the y-intercept, the x is being set to 0, right? So we get f0 equals to log base 2 of 4 minus 3. Now we see this 4 here. We see this 4 here as 2 squared. Log base 2 of 2 squared minus 3. Right? Now then we see, oh, log base 2 of 2 squared. According to our basic property, that's equals to 2. Minus 3, that's 1. So our y-intercept is 0, negative 1. Okay. Then how about if we have natural log of e to the natural log of x squared. E to the natural log of x squared. If we think about this, this is e to the log base e of x squared. Okay, but e to the power of log base e, b to the power of log base e will cancel, and therefore we will get this is equal to just x squared. Okay. Now let's go to other properties of log, the ones that you need to memorize also. Of course, we also need to memorize. But in this section, our textbook actually emphasizes on these three big properties. Okay, let me start from here. Properties of log. There are three of them, and I will call them that way. There are three of them, and I will call them that way. The first one. So I will name them according to the number. The first one is, I need to say first, for the base has to be positive and not equals to 1. And mn, you will see I use this for the argument, has to be strictly greater than 0. Okay, then log base b of m times n is equal to log base b of n plus log base b of n. That's the first one you need to memorize. Log of product equals to sum of logs. Log of product equals to sum of logs. I will prove that number 1 later on. Number 2, log base b of the quotient m over n is equal to log base b of m minus log base b of n. Now the third one, log base b of m to the x, and this x can be anything. Okay, there's no restriction on the x here, equals to x log base b of m. Now, you need to memorize these three properties. I will show you the proof for the first one and the third one. The second one is actually similar to the first one. That's why I won't do that. Do you need to memorize the proof? No, you don't need to memorize the proof. But by me showing you the proof, I hope you really see what's the relationship between this formula and the property of exponents that we have learned a long time ago. Okay, let's see proof for number 1. Proof for number 1, log base b of mn equals to log base b of m plus log base b of n. The proof. I will start with by calling this by certain name. Let me call that, maybe I call that P, and I will call this Q. Okay? So let P equals to log base B of M, and Q be log base B of N. Then what will M and N be? The M will be B to the P, right? And the N will be B to the Q. That's just the consequence of the exponential form from that log form. Now I go on. So what will m times n be?
P plus Q.
M times n?
B
to the p times b to the q. Is it right?
Yeah.
Okay. Which is equal to, if I multiply common base, then we add the exponent. That's b to the p plus q. That's what m times n equal to. Now then I change this into log form. So in log form, log base b of m times n should be equals to p plus q. Right? Now then I put that p and q back, log base b of m n equals to log base b of m plus log base b of n. That's what we already proven. Okay. That's for the first one. Let me prove the number 3 here. Proof number 3. Log base b of m to the x equals to x times log base b of m. Now you will see the proof is actually quite similar, but not super similar. Similar enough. I will call let p be log base b of m. Then guess what? We'll change it into exponential form, b to the p equals to m. Is that right? Now, what we need is m to the x. That's what we need, m to the x. If b to the p equals to m, then m to the x will be equal to b to the p to the x. Is that right? By power rule, we know b to the p to the x, that's basically b to the px. By power rule. Now then I change that back into log form. So log base b of m to the x equals to px. I will substitute that p back. This is x times log base b of m. Okay, that's the proof from the first one and the third one. You don't need to memorize the proof, but I need you to be able to apply that later on. You need to memorize the properties. You don't need to memorize the proof. Okay, but it will be nice if you memorize them. Now let's do some examples. In fact, I will first train you with the intuition. Okay, and then we'll do some problems doing it long way. After that, we'll do problems doing it short way. Okay, let's start looking at your textbook, page 368. For example, number 2. Log 40 plus log 5/2. What will that equals to? Now, according to rule number 1, this is log of 40 times 5/2, which will be log what? I hope you don't use calculator for that. What's that?
10.
20 times 5, 100. And log 100 is equal
Two.
to 2.
2.
Okay, so actually from the last step, I basically use basic property number 3. Okay, because I see that log 100 as log base 10 of 10 squared, right? Okay, now that's for number 2. Let's see number 4. Number 4, log base 9 of 25 minus log base 9 of 75. This is equal to, using property number 2, log difference of logs equals to log of quotient. So the base is 9. So we get log base 9 of 1/3. And then how do we solve this? There are a couple ways to do this. You can answer this directly though. So the way you see is like, if I call that x, log base 9 of 1/3 equals to x, then 9 to the x equals to 1/3. That's 3 squared to the x equals to 3 to the negative 1. 3 to the 2x is 3 to the negative 1. X, 2x equals to negative 1. X equals to negative 1/2. Right? So the answer here is negative 1/2. Now another way to see that, okay, notice that 1/3 can be written as 3 to the negative 1, right? So using property number 3, negative, that's equals to negative log base 9 of 3. Now then, 9 to what power equals to 3?
2.
Almost right.
2 over
1/2, right? 9 to the 1/2, the square root of 9 is 3. You see what I mean? Okay, so that's the 2 different ways to compute that number 4 toward the end. I prefer to say there are 2 different ways to compute this log base 9 of 1/3. One, you go on directly, or you see that as to the power of negative 1 first, and then you see, oh, you know what, log base 9 of 3, 9 to what power is 3? That's 1/2. Okay, so there are 2 different ways to do that. This is one way, that's another way. But the first way takes longer explanation. The second way, shorter explanation. Okay, either way you get negative 1/2. Now, how about number 8? These are still the basic one. How about number 8? E to the ln 3 plus e to the ln 2 minus e to the ln e. Using basic property number 4. E to ln 3 is 3. E to ln 2 is 2. And e to the ln e is e. So the final answer will be 5 minus e. Okay. Now don't forget, this is what we call exact form. This is what we call exact form. If you want to know what's the approximate form, then you use calculator. Can you use calculator for this? Try it. I think you should get 2.2 something. But round it to 5 decimal places instead. Minus with the e. That's e to the 1. 2.28172. This is 2.28172. This is the exact form or exact solution. This is the approximation. Okay. Well, basically, I want you to know how to use your calculator in case that you need to approximate them. That's for number 8. Let's go on. Still on the same section. But we will apply the properties even further now. Write as a single log. Write as a single log. For example, the easy one first, number 12. 2 log base 10, okay, I omit the 10, minus 3 log y. Now, when we say write as a single log, we want that to have log something only later on. Okay, at the end, you have only one single log of something. Now, how to do this? We use property number 3 first to make it log of x squared minus log of y cubed. And then we do property number 2. We get log of x squared over y cubed. That's what we have now as a single log. Okay, that's for number 12. I think that one is quite easy. Number 14. P log base b of a minus q log base b of capital B plus r log base b of C. And this will be, I think I will use property number 3 first. So I can pull the exponent, the coefficient becomes the exponent. Okay, so that's log, that's log base d of a to the p minus log base b of b to the q plus log base b of c to the r. Okay, that's what my property number 3 is doing. Now, I actually wanted to do this problem earlier. Eventually, I will do this type of problem because after this, we'll do a lot of shortcuts. Furthermore, the first 2 terms here, I will put them together. Okay, I will use property number 2. Okay, so using property number 2, I will get log base b of a to the p over b to the q. You right? Rule number 2, property number 2, difference of logs is log of quotient. And then property number 1, using property number 1, because now we have sum of logs. So sum of logs is log of product. A to the p over b q times c to the r. I'm actually done here, but let me write it nicer. This is equal to log base b of a to the p, c to the r over b to the q.
You can't simplify the exponents?
Simplify like what?
Log base b c to the r, isn't that r times log base?
Oh, then you will go back to here. You'll go back, yeah, right? Yeah, if you do that, then you'll go back to here.
Okay, sorry.
Okay, so no, that's fine. Actually, eventually we'll do that. Okay, yeah, but if that's what you do, you will go back there. What they want us to do is to put them in a single log. Okay, if we need to break, if we want to break up the logs, then that's what we do. What you said just now. Okay, now here's the thing though. I want to show you some shortcut. Now, how to see that shortcut now? Let's take a look on the coefficient. If the coefficient is positive, like in this case, the p and r, if it is positive, then notice that it will be on the exponent. Do you see that? On the numerator, I should say. The exponent of the numerator. While if the coefficient is negative, like in this case, negative q, then the q will be on the denominator. Okay, now with the corresponding argument. So p is the coefficient for argument a. So the p later on will be the exponent for base a. And here r is the coefficient of argument c. Then c to the r will be on the exponent. The b is the argument. B is the argument for negative coefficient. Now notice that this b will be at the bottom. Now, why do I want to teach you this? because we want to do it a lot faster. Let's say, for example, if I have number, let's say number 16a. Let's say number 16a, we have log of x squared minus 16 minus 3 log x plus 4 plus 2 log x. Can we do this in one single strike? Yes, it's possible. You see, it would be log base 10, right? It will be log base 10. Now, this x squared minus 16, will that be on the numerator or denominator?
Numerator.
It will be on the numerator because the coefficient is positive, right? Okay, now then how about this x plus 4?
Denominator.
Denominator with exponent?
-3. With exponent 3s, I'm sorry.
Yeah, exponent will be 3 and the negative means it's at the bottom, right? So it will be x plus 4 cubed here. And how about the last one, x?
X squared on the numerator.
X squared on the numerator. Okay, now then from here, so we are actually done. If you think about it, we are actually done. Anything after this is because I see that x squared plus 6 minus 16 is factorable, and we can cancel something later on. That will be log will be log. One of the x plus 4 cancel, so I get x squared x minus 4 big over x plus 4 squared. Is it okay? Now that's for 16a. And can you try 16b? I hope you see the difference and therefore be able to execute the difference. That's log of x squared minus 16 minus 3 times the sum of log of x plus 4 plus 2 log of x. Okay, let me give you 1 minute to put them together and another 1 minute to simplify. Okay, so this will be log of x squared plus 6 on the top. I mean x squared plus 16 minus 16 on the top. For x plus 4, it is at the bottom with exponent 3. How about the x?
It should be at the bottom.
It should be at the bottom. Why?
Because before the negative sign, these two would be log x plus 4 and log and 2 log x would be considered one log. So when you multiply the when you distribute the negative sign, they both.
Yeah, that's right. Because of distributing the negative 3 makes the coefficient here becomes negative, right? Yeah, if we distribute the negative 3,
So we have to distribute the negative.
Yeah, we just need to distribute the -3. Oh, the 3 is outside of the bracket though.
Yeah.
Right? Yeah, the 3 is outside of the bracket, so it becomes -6 later on. So if you will see if you distribute, it becomes -6 log x. Is it right? So you will have x to the 6 now at the bottom. Oops. Now, then from there, we simplify a bit further. This is log, the way we did it earlier, x plus 4, x minus 4. At the bottom, I have x plus 4 cube, x to the 6. So this is equal to log of x minus 4 over x to the 6 times x plus 4 squared. Okay. Now, you try number 18. I give you 2 minutes. Natural log of x cubed minus 1 minus natural log of x squared plus x plus 1. By the way, as I remember, you will not see exponential function, logarithmic function that much until you get to calculus 2. Now, my problem is, you know that I teach calculus 2 this semester, and last semester too, and last year too. So I can tell you this, plenty of students coming to my calculus 2, they cannot do the log fast, and I don't know how to teach them. I mean, at times I lost my patience because apparently their pre-calculus teacher didn't train them well enough. Like the question they know how to answer are very easy ones. And even very easy, it took them like 5 minutes. I ran out of my patience, you know. Okay, so that's why I need you to be good here. Okay, 1 minute. Okay, I think the first step is easy. That's natural log of x cubed minus 1 over x squared plus x plus 1. Okay, but the thing that I really need to know at this time is you need to know to factor the numerator, right?
Right.
And that will be x minus 1 times x squared plus x plus 1. Difference of cube. Okay, difference of cubes. A cube minus b cube equals to a minus b, a squared plus ab plus b squared. Okay. Then if you go on, you see one of the factor cancel, and we are left with x minus 1 as the argument. Now, I hope then we are ready to go on. Let's see. Number 22. Just do it fast. Number 22, the question is write as sum and difference of simpler log. Write as sum or difference of simpler log. Number 22, part 8. Log base b of, what's that? Square root of what minus x squared over x. Now, our textbook doesn't use that parenthesis, the way I see, if my argument is a fraction, I will use parentheses just to avoid misunderstanding. Because here's the thing though, I need you to be aware with this. Log of A over B is different from log A over B. Now you see the line here, just because it's slightly longer, but it covers a little bit, it means this, right? Okay, while what we tried to write was originally log of the quotient, but then the way we write the fractional notation a bit too long, and it means something totally different. No, that's not what we do. Okay, that's not what we do. Now, to avoid that kind of misunderstanding, then I usually put a parenthesis on the quotient. That's what I usually do. Okay, now let's continue. Then that question, okay, that would be the numerator has exponent 1/2 log base b of 1 minus x squared minus log base b of x. Okay, actually for that one we are done. But if you happen to see that you can factor this, then you should go on. And this is 1/2 log base b of 1 plus x plus 1/2 log base b of 1 minus x minus log base b of x. Okay, now that's for part A. Part B, natural log of x times cube root of 4x plus 1 over square root of 2x minus 1.
A quick question.
Uh-huh.
Would a question like for 22A, like find the domain and the range?
Yes, possible.
Possible?
Yeah, possible.
So would you look?
I will explain it later.
Oh, okay.
Yeah, I will explain it later. The emphasis of the domain you can see a lot more in 5.5. So that's why I'm not really rushing into answering it right now.
Okay.
Yeah, okay. But let me finish this one. This is equals to natural log of x. I hope you can see that. And then how about for this?
1/3
Plus 1/3 of natural log of 4x plus 1. Then this guy here.
minus half log natural log 2x minus 1.
Minus 1/2 natural log of 2x minus 1. Good. Okay. If you don't see that pattern, of course, just to do this one problem will take you extra 1 or 2 minutes, which I don't think is necessary. Okay. Now, we are actually done with this section here. Let me give you the suggested homework. Suggested homework for 5.4. We'll will be number 1 to number 25, 1 to 25, and then continue on number 43 to actually I have one more, I forgot. 43 to 50 to 61. 43 to 61. I forgot to mention about change of base, by the way. Change of base is this. It's actually quite simple. Change of base. For B and P greater than 0, B and P not equals to 1, we have the following. Log base B of M, of course the M has to be also be positive, okay, that can be written as log base P of M over log base P of B. Now, like what I said before, this enables us to compute by calculator, to use calculator to compute certain log value, which we will need on Thursday. Let's say, for example, if I need to compute, let's say, for example, I need to compute log base 3 of 20. Now, most of the time, your calculator doesn't have base 3, especially if you use TI-30 or TI-36. Okay, you don't have base 3. So on our calculator, we only have base 10 and base E. Now, suppose I change it into base 10, it will be log base 10 of 20 over log base 10 of 3. That's if you change it into base 10. If you change it into base E, you will get the same answer at the end. Natural log of 20 over natural log of 3. Okay, either way, you will get the same answers. That's for 5.4. Did I give you suggested homework for 5.3? No. 5.3, let me continue here.
You gave us 5.3 already.
Did I give?
Yeah, last time.
Not this time though. What number did I assign you for 5.3?
5.3, 9 through 11, and 17.
Oh, no. You need more. You need more. That's from the last one. The current one, I need you to go on for 5.3. I need you to do number 21. Number 23 is good for your instinct. Number 25, 27. And then 30. Actually, let me just say from number 21 to number 39. 21 to 39. Okay. Now, I would like you to read, to watch the lecture video. So beside this suggested homework that I expect you to do, to speed up our lecture next time, and that will be the one going forward. I need you to watch the lecture video from SMC. I posted on YouTube. The SMC YouTube thingy. SMC YouTube, the one that you need to watch, will be the one on section, I think that will be section 4.4 and 4.5. Yeah, you need to watch the one from 4.4 and 4.5. Okay, if possible, go on further to 5.1. Well, anyway, at least right now you are parallel to, you are not parallel, but what we have done here is the same to what they did there for 4.3. Okay, so 5.4 for us, our 5.4 is equivalent to their SMC's 4. I think they're 4.5. Hold on. Let me see the book. Give me a second. Yeah, it's there's parallel to their 4.5. So when I go on to our 5.5 and 5.6 on Thursday, that's the same to SMC 4.6. And after their 4.6, I will do chapter 6, which is trigonometry. Okay, so this Thursday we will finish chapter 5. This Thursday we'll finish chapter 5, and hopefully I can introduce you a little bit with trigonometry. Okay, that's for today.
Question?
Yes, huh?